The more interesting, the deeper thing about this definition is that it is the first definition that is properly inductive. That is, the first one where the type that we're defining appears as an argument to one of the constructors. And that means that the set of trees that this definition picks out is an infinite set. They are all very tall and narrow trees, consisting of lots of S's with an O at the bottom, and you can see that from the type. Okay. And here are the Arabic numerals. Nothing too surprising about it. It's really just a hack in the parser and printer. Okay. Now that we have properly inductive data types, we need properly recursive function definitions, and we get those by replacing the keyword definition with the keyword fixed point. And then we can define things like, is this number even? We can define multiply, subtraction, etc. One slightly interesting thing about this definition is that here we're pattern matching against pairs of numbers. And in the patterns, correspondingly, we have pairs of patterns. Okay, and we can introduce the usual plus, minus, times symbols to make arithmetic expressions over natural numbers easier to read. All right. Oh, I see a question. Thank you so much. I see 2 questions. Wow. Okay, excellent. Thank you.
From the point of view of using any kind of computation in coq, isn't it slightly problematic that decision natural is unary rather than binary? I understand that it's very useful for proving theorems, but if you are going to represent anything in memory that is not, if you want to write any non-trivial theorem involving integers and you take the wrong canonical representation, it will make your proofs very inefficient.
This is very true, and let me repeat the question because this is getting recorded. The question is, isn't this might be fine, this representation of numbers for proving things? In fact, I agree, it is fine for proving lots of things, but wouldn't it be terribly inefficient if you actually tried to compute over these numbers? And the answer is yes, it would. And so when people use coq for writing programs that they intend to extract and use for real computation, they will do one of 2 things. Sometimes people just write their program using natural numbers, but then they tell the extraction machinery, whenever you see nat, please map it to, say, the Haskell big integer type, or indeed the Haskell word size integer type. And that is a perfectly legitimate thing to do. People do that very commonly. A different thing you can do, though, is you can define in coq your arbitrary size binary numbers or your fixed size binary numbers, and then extract those in a smarter way. And that will even speed up computations within coq, which is often a good thing. So the coq standard library and a lot of user-contributed libraries include many different representations of numbers which are useful in various circumstances. We will only use nat for the next few days, but you'll see some of the others over the next 2 weeks. Another question.
Previous slide, please.
Previous slide.
There are quoting marks there. When you should use?
Yeah, so when do you need to use quote marks with the notation? So my system is, I always put quote marks around the whole thing that I'm defining. And then if there are symbols in there, they will be treated as part of the syntax automatically. If you want to have keywords in there, then you need single quotes inside of the double quotes around your keyword symbols.
Okay, thanks.
So you define the associativity here, but back on the OR, there was no statement about associativity.
Right.
But then you had a compound OR, and it knew how to do the associativity.
Okay, so what about these associativity things? The observation is that here we're explicitly declaring the associativity, and when we defined OR, we did not. So when we defined OR, we were getting the default associativity, which I guess must be, well, it doesn't matter with OR, does it? It only matters with minus, really. That's the one that you have to be careful of. Plus and times and or and are commutative and associative anyway. So, so for minus, it is important that we say left associativity. And then these levels have to do with parsing. They have to do with the precedence of parsing. And this is all a little bit complicated. You can look it up in the coq reference manual if you really care, or if you're defining your own new notations, which you will do eventually. But for the next few days, you don't need to worry about it. We'll define the ones that you need. Other questions? Let's go on. Okay, here's the less than function. So what? Here are proofs. We've seen proofs already, actually. We wrote little proofs of our unit tests. But they were kind of ridiculously simple proofs because there was nothing abstract, there was nothing quantified about the claims that we were making, so we could evaluate the truth of those claims just by simplifying. So this brings us to the other half of coq. So coq you can think of as a combination of two things. This functional language, Galena, and then a whole set of tactics, a tactic language that is used for guiding a stateful proof checker through the steps of validating claims that we make. So we can write down theorems, and then the keyword proof signals to the top level that now we're going into a mode where we're checking a claim that we've made. Each command that we then give, they're called tactics, should be thought of as an imperative command. So although coq's programming language is functional, its tactic language is very imperative. So we're guiding this, we're manipulating the state of the proof checker to gradually knock out all of the goals that have been raised during the checking of this proof. And when we get to 0, then the proof is checked, and we can say QED. Now, in a day or two, we'll talk some more about the fact that actually those two sides of the coq universe are not really so different as the way that we're talking about it now. But even so, it's a useful fiction, and it is the way that people think about getting work done in coq most of the time. So let's maintain that fiction for now. Okay, so checking the time. I'm just going to keep blitzing on forward and let people ask questions. So we have very simple proofs. The only interesting thing we're introducing is the intros keyword that allows us to move quantifiers from the goal statement into the premises of the proof, into the hypotheses. Let's see. Okay, and now we have the rewrite tactic, which says take an equality that we already know and take a goal statement that involves something that you find on one or the other side of that equality and rewrite it, replacing that one by the other side. And rewrite can be used in both directions. So the default is left to right, but if you say rewrite arrow going left something, then the equality something, then the right-hand side of the something equality will be replaced by the left-hand side in the goal. Rewrite can be used not only with hypotheses from the current context, that is, hypotheses that we've introduced in the statement of the theorem that we're trying to prove right now, but also named things that are that we put in the context by naming and proving theorems earlier on. Next tactic is called destruct, and this is the tactic that we use for case analysis. So if we have something in the context that says, say, B is a Boolean, and we need to do reasoning by cases. So is it true? Then you think about it this way, and is it false? Then you need this other way of reasoning. We split the current goal into a case for true and a case for false, or if we destruct a number, a case for 0 and a case for successor of something, by saying destruct of the thing in the context. And this is also the place where we introduce the notion of bullets for structuring proofs that involve many subgoals. You're going to develop your own habits about how pedantic to be about inserting bullets. I find that if I know that there's going to be a destruct, and then each case is just going to take a couple of little tactics, and then it's going to go away, people often ignore putting in the bullets for those sub goals, and it's probably fine, but it's really easy to get confused. So as you're starting out, I recommend putting in all possible bullets. Every time you see that a tactic has generated multiple sub-goals, put in bullets. And then if you find that that's too annoying and too many bullets, and you don't want to do it later on, you can leave them out. It also depends on, sometimes you're working in a more exploratory mode, just trying to find out as fast as possible if something is true. Sometimes you've established that something is true, and now you want to go back and make your proof script more robust. That will often involve not just tidying it and putting in comments and whatever, but also introducing some automation. And trying to crunch it down so that if the definitions change a little bit, the proof will still execute. And that's something that we'll come to later on in this tutorial. Not today. Question?
Yes. If you have a case that's vacuous, how do you deal with that? Or a case that's not actually feasible, because I've tended to get stuck there.
Excellent question. So what if you do a destruct and you wind up with some vacuous or nonsensical cases? That often happens. It's very common in paper proofs also. And in a paper proof, you would just say this can't happen. But if you unpack that a little bit, generally it can't happen because there's an explicit contradiction now someplace in the hypotheses. Right? So by doing the destruct, you've somehow, in one branch, introduced a hypothesis that black is white. And you need a way now of kind of getting the juice out of that contradiction to prove the goal. The way that the tactic that does that is inversion, or often destruct will do it. So, and we'll come back to that. So save that question for a little while. But destruct or inversion is the short answer. Other questions? Okay. All right. We can nest bullets, and if you run out of bullets, if you get very deeply nested, if you find yourself running out of bullets very often, it's probably a sign that you need to take some fact that you're establishing very laboriously in the middle of the proof and break it out as a separate lemma. So usually 3 levels of bullets is really plenty. Occasionally, you will need to go much deeper, and then you can use curly braces that kind of reset the bullet nesting. All right. And then one last thing is that, which we use a lot, is this notion of intros patterns. So destruct, I didn't say it explicitly, but you've read it in the chapter. Destruct takes a pattern in general, destruct takes a pattern that says what names should be given to the variables that are being introduced to represent the sub-expressions of the tree that you're destructing. So the destruct just takes the top-level constructor and considers all the possible cases. In cases where that constructor may have taken an argument, like with Nat, the successor, you need a name for the subtree, and it will be introduced automatically for you if you don't use an as pattern, and it will usually not be a very nice name. So coq tries to be a little smart, and you could argue that its choices are not pessimal, but they're not optimal either generally. So, so it's good practice to introduce your own names. And in fact, this is probably an example of a bad usage. This is a case where we're destructing a variable y, and it appears to be from some type that has two constructors. The first constructor doesn't have any arguments, so the left-hand side of the vertical bar, we don't need any variable names. And the right-hand side, we've reused the name y for the name of the sub expression. And I actually often find that confusing myself. So if I were fixing this, I would add in a prime on those y's, the second and third ones. Okay. All right, and that's the end of the basics chapter. Any last questions? Please.
So in case we want to discuss more modules, how to use them and something maybe anything modules, whom should we talk to?
Who should you talk to about how to use modules? So the best place for information about coq that isn't in the Software Foundations materials is Adam Chapala's book. And the best place after that is the coq reference manual. So the coq reference manual, those of you that have already had a look, you will see that it could use some work. It's been kind of, various bits of it have been written by various overworked and underpaid grad students and professors over the last 30 years. And it kind of shows it. So in the last round, the coq team is aware of this. In the last round of upgrades to coq, the manual was moved from its clunky old LaTeX version to a spiffy new Sphinx version that generates nicer looking HTML and that is easier for community members to edit. And then the plan is to actually make it read better as well. This is a good moment for me to make another request to you. All of you are in a rare position as members of the coq community. So you are now members of the coq community, but you don't know too much about coq yet. That's a golden position. It's only going to last for a few days. So my request to you is, if you find yourself looking at the reference manual or indeed looking at anything in Software Foundations or any place else, please notice when there are things that you don't understand or that don't make sense or that could be said better, and either tell somebody or, better yet, write it better yourself and submit a pull request. The coq team is very happy to have pull requests on the documentation, and it's a very good way to get involved in contributing to coq without the hairiness of getting involved in the implementation. So, so please take it on yourselves to help improve the materials that we share. Please.
Particularly at last year's event, some people got together and started writing a lot of new
Oh yes, I should say that. The reason that the documentation is now in Sphinx instead of the bad old LaTeX version is because of last year's summer school. Somebody at the summer school said, oh, I see something that we could do to really help move the ball in the coq community, and it's going to take a lot of effort, so we should do it together. And they assembled about 20 people from the summer school to sit down and do the translation of the documentation. Please.
I have a question about the coq IDE. I learned a little bit Isabel for the new coq, and there is a proof state panel which shows the current subclause and refresh in real time. And when I use the coq IDE, I think that left upper panel is the subclause panel, is it? But there is nothing displayed on my computer. Is it common to everyone, or?
So this is a question about coq IDE, and the question is, it seems that the panel where the subgoals look like they should appear isn't actually displaying anything. That sounds like a question to take up with somebody during the break. But My experience, I don't use coq-IDE very much, but my experience using proof general is that